but to talk about the time value of money. Now, you all know about inflation, right? Inflation's a big thing in the news these days. Prices are going up and up and up. Go to the grocery store to buy your, I just noticing it the other day, wanted to go buy my, well, sometimes I get Lucky Charms, but a couple days ago, I got Reese's Puffs, the giant size box. Used to be able to buy it for like $5 something. It was $6 something. Okay. So we see it, we feel inflation by prices going up. Another way to think of it from an economist perspective is that the value of a dollar is going down. You can't buy as much with it as you used to be able to. Is the time value of money related to inflation? In part, but that's not the only cause of the time value of money. What is the time value of money? It can be stated simply that $1 is worth more today than in the future. Why? Well, in part because of inflation. I want to buy that box of cereal today. It's cost $6 something. You know, in a month, it could cost $7 something. So I better buy it today. And if I want to eat it next month, I better just save it in my cupboard. Okay. But it's more, even if there were no inflation. And as it was, you know, in the 90s and the 2000s and early 2010s, there really wasn't much inflation, right? Maybe 1 or 2% per year. That's pretty low by historical standards. Time still has money still has a time value, even in that kind of situation. Why? Well, you might say it's because we're greedy. Somebody says, I'll give you $1 today, or you can wait for next year. Or to make it even more profound, somebody says, I'll give you $1 million today, or you can wait till next year and I'll give you $1 million. Right? Then it's even more clear. I'd rather have the $1 million today. Give it to me now. I might not be alive in a year. I really want to go buy that sports car right now. I don't want to wait a year. Right? So even if there weren't inflation, money would still have a time value. The person could say, well, I'll give you $1 million today, or I'll give you $1.1 million in a year. Which would you take? You might say, yeah, $1.1 million, that's 10% growth. I'll wait a year. You would then say those two monetary amounts are equivalent relative to a 10% interest rate. Right? $1 million today versus $1.1 million a year from now. That's a 10% change in monetary value. You could say at a 10% interest rate, those two monetary amounts at those two times today and a year from now are equivalent. Let's get into details. The future value of $1 paid right now, T years from now, where T could be 1 or 2 or 1.5, is represented as 1 plus I to the T dollars, where I is essentially an interest rate. Do we have to be thinking about bank accounts to make sense of I as an interest rate? No. You could think about it from a purely modeling perspective when I'm trying to model the time value of money. Of course, different banks have different interest rates. Different investments have different rates of return. Some, like the stock market and like cryptocurrency, are very volatile, and it's very difficult to say what the rate of return is going to be over the next year. People try, but they're usually wrong. But if you are sort of trying to model the economy, say, from a broad perspective, you might sort of lump all those kinds of investments into this I here that you see to model future values and present values. The present value of $1 paid T years from now, right now, is therefore, what would it be? Pretend I is 0.1 and T is 1. This would be 1.1 to the first power, which would be 1.1. That would represent 10% growth. If we think about $1 being paid in 1 year in the future, and we want to think about what's its present value, what would I do instead? I would divide by 1.1 to the first power. In general, divide by 1 plus I to the T power. which, as you know, by definition of negative exponents is the same as 1 plus I to the negative t power. And you could also think of it as v to the t if you define v to be the reciprocal of 1 plus I to the negative 1, which is, of course, the same as 1 over 1 plus I. This is all standard notation you'll find in actuarial science books. I haven't looked in finance books that are not explicitly actuarial science, but maybe they use similar notation. I is called the interest rate. V is called the discount factor. The word periodic is in there. If time is measured in years, as it most commonly is, this would be an annual interest rate and an annual discount factor. So no probability in statistics here. Essentially, this is just compound interest, you might say. But we're thinking more broadly in terms of this bigger idea of time value of money. We do want to come back to probability and statistics, okay? We want to come back, in fact, to survival models, survival type random variables. Why? Because insurance companies have to think about money. Think about life insurance. Life insurance policies, there's various kinds. The most common kinds, terminology is whole life policies and term life. Whole life is technically simpler. You buy a whole life policy, or your parents buy you a whole life policy when you're 20. Technically speaking, if you do such a thing, you pay premiums. I pay premiums every quarter. I do have a small whole life policy. I pay premiums every quarter, every 3 months. And you pay those if you want to keep the policy for the rest of your life. And there's a defined benefit at death. Though with a whole life policy, you can get some money back earlier if you want to cancel the policy. The insurance company is thinking about the fact that they're getting some money from you. It's called premiums. So they're taking money from you, but there's a catch. They have to pay money to your beneficiaries if you die. Your spouse, for example. But they don't know when you're going to die, and neither do you. Only God knows. So it's kind of like a bet, you might say. They're trying to think about how risky are you of an investment to get money in and then pay money out to your beneficiary when you die, yet they still make money on you, hopefully. Now, of course, if you don't pay any premiums and you die right away, they're gonna lose money on you. But most people would not die right away. They therefore have to think about present values, especially if you've got 60, 70, 80 years to live. They got to think about investing the money that they take in from you, and they are allowed to do that. They are allowed to invest it. They have to think about the time value of money. Not quite to relating this to probability yet. Some more terminology. Given an interest rate I and a corresponding discount factor V, remember V is 1 over 1 plus I. So if I is 0.1, V would be 1 over 1.1, which would be 0.9 something. We define the force of interest, also called the continuous periodic interest rate, by this equation. Delta is ln of 1 plus I. Delta is called the force of interest. In a calculus class, is called the continuous interest rate. And I think in our calculus book, it's typically called K. But in actuarial science books, they call it delta. If I is 0.1, then delta would be the natural log of 1.1, which is a little less than 0.1. Natural log of 1.1 turns out to be about 0.095. So if you want to think of this in terms of interest rates, like for a bank account, because it's just simpler to imagine, if you had a bank account that paid you 10% interest, wow. Actually, I had a savings account in 1982 that paid me 8% interest. I'm not joking. Of course, inflation was really bad back then. even worse than it is now. If I is 0.1, 10% annual interest rate, then ln of that is of 1.1 is 9.5% essentially. The corresponding continuous interest rate is 9.5%. You might remember from calculus that kind of relationship happening. I don't want to get into details about why it's less. It's related to slopes of tangent lines. Remember, v is 1 over 1 plus I. In other words, 1 plus I to the negative 1 power. So using a property of natural log, of logarithms in general, you can bring that negative 1 power in front. And also write this as the opposite of natural log of v. But v is less than 1, so this is a positive number. It's equivalent to 1 plus I to the t being e to the delta t and v to the t being e to the negative delta t. Why do we do this? Essentially just because, relating this to e makes things easier to integrate. This is called the instantaneous relative rate of growth, assuming I is positive. And then delta would be positive. Hang with me here. Doing okay? Now we're on to thinking about probability and insurance. There's something called the net single premium, NSP. Suppose capital T is a future lifetime of a newborn baby, a random variable, a continuous random variable that's modeling the lifetime of a newborn baby. When I say that, as I've emphasized before, that means behind the scenes, this has a distribution, some hypothesized distribution. There's a PDF, there's a CDF, there's a survival function now we know, where there's also a force of mortality. All those things are behind the scenes in this statement. We can define a random variable. Here's the hardest concept for today. That is the present value of a future $1 benefit paid at time capital T when the baby dies. Hopefully as an older person. This is called a continuous insurance random variable. But what is it? What's it? Does it have a formula? Yeah, we can relate it to capital T. It's v to the capital T power, which would be the same as e to the negative delta times t. And it's got a special symbol in actuarial science called z bar. Remember how I said z in probability and statistics almost always means standard normal random variable? Here it does not. This is not standard probability and statistics. This is actuarial science. What does the bar mean? Why is there a bar above it? I've not found a definitive answer for that in any book. My gut intuition is they do that because it's continuous random variables. There's a corresponding discrete one that doesn't have a bar above it. It does not mean, if you know about statistics, it does not mean a sample mean. Z is not standard normal, and this is not a sample mean. We're going to learn about sample means as statistics in chapters 6 and 7. This is just actuarial science notation. Actually, the deeper you get into actuarial science, the hardest part about it is the notation. The notation gets really crazy. You can look it up, Google it, actuarial science notation. You'll see some sheets with really crazy notation on it. But the ideas are very much related to what we're learning in improv and stats. So this is just a new random variable. T, capital T is a given random variable. If we know what delta is, we can create this new random variable, call it z bar, based on the value, based on capital T. Think about observed values. This is a theoretical kind of equation, but you can think about the corresponding observed values. This newborn baby lives 80 years. The observed value of capital T would be 80. E to the negative delta times capital T is going to be a number pretty close to 0, right? If capital T is 80, even if delta is small, like 0.02 or something, 0.02 times 80 is, 0.01 something. Excuse me. 1 something. Do that right. 0.02 times 80, I guess, would be 1.6, wouldn't it? This would be e to the negative 1.6, which is going to be not super small, but definitely less than 1. If delta is moderately large, like 0.05 or 0.1, then this could be really close to 0 if the baby lives a long time. So the observed value of this will be pretty close to 0. The present value, this is a present value, the present value of a $1 payment at the time of death is going to be close to 0. The fair price, quote unquote, to pay for such coverage is called the net single premium, and it is the mean of Z bar. And it's called A bar. I think the A here, I did read somewhere, stands for actuarial. It's sort of like actuaries taking ownership of this concept and saying, this is a fundamental thing in actuarial science. A bar is the mean of Z bar, and by, remember, generalized expectation? We're taking the expected value of a function of a random variable here. The t is part of this exponent. In the book, the generalized function that we took the expected value of was called h of x. Remember that? This is like an h of t, you might say. And by the generalized formula for expectation, you still integrate that function, replace capital T with little t, times the PDF. This is the PDF here. Sigma is the survival function. Remember, the negative of its derivative is the PDF. But this quantity here that I'm underlining with my cursor is non-negative, because the survival function is non-increasing. It's either constant for a while or it's going down. So its derivative is negative, making this expression here positive. If you do it for a client, you can use the subscript notation here for a client of age X, and they write A bar X. Keep the concepts clear in your mind. Capital T is a random variable, therefore capital Z bar is a random variable, but capital A bar is a number, not a random variable. It's the mean of Z bar. Yeah, okay. The PowerPoint timings are not doing so well. This can be generalized to clients. I could use the TPX notation here, by the way. And in fact, in actuarial science books, that's the most common thing to use. The negative of the derivative with respect to T of TPX. I could write in actuarial science books, what you would see is A sub X bar, or A bar X, meaning the mean of Z bar sub X, which we could write as e to the negative delta times T sub X, or T of X, I should say, T of X. That's going to be the integral from 0 to infinity of e to the negative delta times, I can replace this T of X with just a plain T, the variable is still T, of the negative of the derivative of the survival function, but it's a derivative with respect to T, not X. Think of X as fixed. You could use partial derivative notation to emphasize that there still is an X in there. And there are some situations where differentiating that with respect to X is relevant. But when you look at this equation, you should think of X as fixed. So you could write it this way too, using the TPX notation. And once again, it's just a formula you can use in your homework, okay? Go ahead and use it. You can use Mathematica to help you do the integrals. And for chapter 5, which we're starting on Thursday, you can use Mathematica to help you do the integrals. Though you may want to do some of those integrals, the double integrals, by hand. We'll keep them as simple as possible. Let me just end with 1 minute here. There is a discrete version of this. Here it is. Notice that we're using K, which is the greatest integer in T. And we're using Z instead of Z bar. And we're using A instead of A bar. Okay. We have to do summations instead of integrals. Your homework, we try to keep the examples relatively simple. Okay. So in the reading and here in class, we did go into theory. Theory that you know, or just trying to relate it to new ideas. And yeah, the net single premium would be of interest to the insurance company. Give me 15 seconds here. It's an average present value of a $1 future premium paid out at the time of death to beneficiaries of current newborn babies. And that would affect how much they want to charge you for those new insurance policies. Of course, they want to make money as well, so they probably charge you a bit more, right? Of course, there's other things that we are oversimplifying, like, is delta really constant? No. We have to make simplifying assumptions and kind of cross our fingers and hope it works. And the insurance company stays in business. All right. See you on Thursday.